Hello and welcome to this revision session for OCR A-Level Physics on the topic of materials. So in today's revision session we're going to look at how to answer examination based questions on the topic of materials. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding for A-Level Physics, understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. And in this left hand side section, write down your working out and answers to the questions in the revision sessions. When you're doing this, make sure to write in full sentences and show your full working out. Whilst in the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for your A-Level Physics? So the first step is to learn the key facts. Use the revision guides, the class workbooks, the student prep notes, the textbooks to learn the key ideas of the course, and you might wish to make mind maps or write out notes yourself. The second step is to retrieve your understanding, so test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you might want to do this from cue cards. Then the third step is to practice examination style questions, so use exam prep books, homework books, study books, additional workbooks to answer exam questions and mark your own work. Now you may wish to download your own past papers to do this. So the three steps of revision are to learn the key facts, to then test yourself, and then to practice examination style questions. So in this revision session today, we're going to have two types of questions. So we're going to be looking at general check questions. So what we're going to be focused on in this revision session are the basic questions designed to probe your understanding and knowledge of the key concepts of the topics that we're going to look at for materials. So let's now have a look at this idea in our different concepts for materials. So the first question says, a cube of copper has a mass of 240 grams. Each side of copper is 3 centimeters long. Calculate the density of copper in grams per centimeter cubed in kilograms per meter cubed. Then the density of steel is 7,850 kilograms per meter cubed. Calculate the mass of a steel sphere of radius 0.1 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to work out the volume of the cube because density is mass over volume. So we can say that the volume of the cube, because it's a cube that all have the same dimensions, it will be 3 centimeters times by 3 centimeters times by 3 centimeters, which is 27 centimeters cubed. Density is then mass over volume, so it's 240 grams over 27 centimeters cubed, which is 8.89 grams per centimeter cubed. To then turn that into kilograms per meter cubed, we've got to multiply by 10 to the 3 to go from grams into kilograms, divide by 10 to the 3 to get from grams into kilograms, but then we're then also going to have to divide by 10 to the minus 6 there, because we're going from centimeters into meters. So we're going from 10 to the minus 6 to 10 to the minus 2 to 10 to the minus 6. So therefore we're going from 4 times there, so it works it through to be 8,890 kilograms per meter cubed. Now in our next question, we know that the volume of a sphere is 4 over 3 pi r cubed, because that is what the volume of a sphere is according to the mathematical equation. So we can then pop in our values. Now again, we do 4 over 3 pi times by 0.15 cubed, so we get 0.0141 meters cubed. We then say density is mass over volume, so mass is density times volume, so we work it through to be 111 kilograms. The next question says, a paving slab has a mass of 73 kilograms in dimensions of 40 millimeters times by 50 millimeters times by 850 millimeters. So calculate the density in kilograms per meter cubed of the material from which the paving slab is made. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, first thing we need to do is we need to work out what the volume of the object is, because we know density is mass over volume. So we do 40 millimeters times by 500 millimeters times by 850 millimeters. We then say that's 1.7 times 10 to the 7 millimeters cubed. We can then go from millimeters cubed to meters cubed by times it by 10 to the minus 9, because we know that from millimeters into meters times 10 to the minus 3, and because it's millimeters cubed, we're doing it 3 times. So therefore it's 10 to the minus 3, 10 to the minus 3, 10 to the minus 3, which is 10 to the minus 9. So we get 1.2 times 10 to the minus 2 meters cubed. At that point we say density is mass over volume, so it's our mass in kilograms, 73, over our volume in meters cubed, 1.7 times 10 to the minus 2, so we get 4,300 kilograms per meter cubed. The next question says, a measuring cylinder is filled with water up to the 70 centimeter cube mark, and a regular mass of 0.080 kilograms is gently placed in the water. The new water level is 85 centimeters cubed. Calculate the density of the rock, and then calculate the average density of a neutron star of mass 3 times 10 to the 24 kilograms and radius 12 kilometers. Then an 18 karat gold bar of volume 3.34 times 10 to the minus 6 meters cubed comprises of 58.2% gold and 41.8% copper by volume. Calculate the density of the bar. Any of the density of gold to be 1.93 times 10 to the 4 kilograms per meter cubed, and the density of copper to be 8.96 times 10 to the 3 kilograms per meter cubed. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we know that density is mass over volume. Now we know the volume is going to be the difference in the water level from when the object was placed in the water when it was out of the water, because the object will displace its own volume in the water. So we know it's 85 minus 70, because that's the difference, so it's 15 times 10 to the minus 6, because we want to be working in meters cubed. So from centimeters into meters, it's going to be 10 to the minus 2, but then we're doing it 3 times, 10 to the minus 2, 10 to the minus 2, 10 to the minus 2, so overall it's 10 to the minus 6, so it's 0.080 divided by 15 times 10 to the minus 6 is 5.3 times 10 to the 3 kilograms per meter cubed. We can assume that a star has a shape of a sphere, so we know that V is 4 over 3 pi r cubed. We know that we work in meters, not kilometers, so it's 12 times 10 to the 3, and at this point we do 4 over 3 times by pi times by 12 times 10 to the 3 all cubed, so therefore it works out our volume. We can then say density is mass over volume, so it's 3 times 10 to the 24 over this volume, so it's 4.1 times 10 to the 11 kilograms per meter cubed. Now in our next question, when we have a alloy, we can work out the mass of each of the objects by doing density is mass times by volume. So we know that the mass of gold is going to be the density of gold multiplied by the volume that we can work it through. So therefore you can work out it's going to be 58.2% of the volume. So it's going to be 0.582 times by the overall volume, 3.34 times 10 to the minus 6, multiplied by the density is 3.75 times 10 to the minus 2 kilograms. We do the same for copper and we get 1.25 times 10 to the minus 2 kilograms. So therefore the density is the overall mass divided by the overall volume. So we add the two masses together to get the overall mass. We then divide it by the total volume given in the question, and we get 1.50 times 10 to the 4 kilograms per meter cubed. Now this does assume that there's no chemical reaction taking place and the average separation between the atoms doesn't change when the objects are mixed with each other. So our next question says, an empty paint tin of diameter 0.150 meters and of height 0.120 meters has a mass of 0.22 kilograms. It is filled with paint to within 7 millimeters of the top. Its total mass is then 6.50 kilograms. Calculate firstly its mass, then its volume, then the density of the paint in the tin. So pause the video now, then unpause the video when you want to go through your answers. Right, so when you're answering this question, you've got to think about the idea of how you work out the total mass. So the mass of the paint is going to be the total mass minus the mass of the empty the empty can, because that's obviously the mass, therefore, of what the can would be. So the mass of the paint is the difference between the two. So 6.50 minus 0.22 is 6.28 kilograms. Its volume, well, we assume that the tin will have a shape of a cylinder, so it's pi r squared h. The value of h is going to be the value of the tin minus 0.007 millimeters, because it's 7 millimeters off the top, so it's 0.113 meters. So then say pi r squared times by h. We work it all through. Now again, remember that it's r and you're given d in the question, so you've got to half the diameter to get to the radius. We then work it through and we get 2 times 10 to the minus 3 meters cubed. Now finally, what's the density of the paint in the tin? Well, we know the mass to be 6.28 kilograms. We know the volume of the paint to be 2 times 10 to the minus 3 meters cubed. So you work it through to be 3,150 kilograms per meter cubed. The next question says, a circular head of a drawn pin has a diameter of 7.5 millimeters. A thumb presses against the head with a force of 8.0 newtons. Calculate the pressure exerted on the head, and then calculate the vertical force exerted by the atmosphere on the surface of a calculator of length 15 centimeters and width 7.5 centimeters. The atmospheric pressure is 1 times 10 to the 5 pascals. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, pressure is force over area. We've got our force. We know our area is going to be pi r squared because it's a circle. We can therefore half the diameter to get the radius, and we convert our millimeters into meters by doing 10 to the minus 3. So we get our answer out to be 1.8 times 10 to the 5 pascals. By the same logic, force is pressure times by area, so we know our pressure is 1 times 10 to the 5, it's the atmosphere, multiplied by the total area. We assume it's going to be a rectangle, so we convert our 15 centimeters and 7.5 centimeters into meters to work out our answer to be 1.1 times 10 to the 3 newtons. The next question says, a chair stands on 4 feet. Each of area 10 centimeters squared. The chair weighs 80 newtons. Calculate the pressure it exerts on the floor in pascals. Then estimate the pressure you exert on the floor when you stand on both feet. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we know that pressure is force over area. So we've got to work out our total area. First, you convert our centimeters squared into meters squared. Of course, you need our answer in pascals, so therefore the area needs to be in meters squared. So centimeters into meters is 10 to the minus 2. So therefore, if it's centimeters squared, because there's 2 of them, it's going to be 10 to the minus 2 plus 10 to the minus 2. So therefore, you can work it through like that. So it's going to be 10 times 10 to the minus 4. There's 4 of them, so you multiply by 4. Pressure is force over area is 20,000 pascals. In this next question, you've got to estimate values. It's very important in physics. So we can estimate the weight of a human to be around 600 newtons, the area of a foot to be about 0.05 meters squared. So therefore, pressure is going to be force over area. So 600 over 0.05 is 12,000 pascals. The next question says, atmospheric pressure at sea level has a value of 100 kilopascals. The density of seawater is 1020 kilograms per meter cubed. At what depth in the sea would the total pressure be 250 kilopascals? Then icebergs typically float with a large volume of ice beneath the water. Ice has a density of 917 kilograms per meter cubed and a volume of V ice. The density of seawater is 1020 kilograms per meter cubed. What fraction of the iceberg is above the water? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the total pressure that's going to be exerted is going to be the hydrostatic pressure plus the atmospheric pressure, because they're both pushing down on the object. So we know what the atmospheric pressure is. It's going to be 100 kilopascals. It says it in the question. Well, what's the hydrostatic pressure? The pressure in the actual liquid. Well, we do rho times by g times by h. So 1020 times by 9.81 times by h. We know that the total pressure, it says to be, is 250 times 10 to the 3. We can therefore rearrange it and make h the subject. So we work out our answer to be 15 meters. Now in the next question we know that if an object floats, we can say that the forces on the object are balanced. So therefore the weight of the iceberg is going to be equal to the weight of the water. Now we know that it's mass times by gravity, and therefore we can say that mass is density times by volume. Now we know we can say rho v g equals rho v g, with one for the ice and for the water. We know that the g's will cancel through, and therefore we can ratio v ice over v water is equal to density of water over the density of ice. So therefore the volume of the water is going to be density of ice times by the volume of ice over the density of water. Pop in all the values, and therefore the volume of ice is 0.9 times the volume, the volume of water is 0.9 times the volume of ice. So that tells us that it's going to have only 0.1 volumes of it above the water, which is why most of the iceberg is below the water, 9/10 is below, 1/10 is above. The next question says, calculate the total pressure acting on a submarine at a depth of 20 meters. The atmospheric pressure is 101 kilopascals and the density of seawater is 1.03 times 10 to the 3 kilograms per meter cubed. Then the density of mercury is 1.35 times 10 to the 3 kilograms per meter cubed. Calculate the pressure exerted by a column of mercury at a depth of 0.765 meters. Then show that the pressure exerted at a depth of 610 meters in water is about 6 million pascals. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, like we said before, we know that the pressure is going to be the atmospheric pressure plus the hydrostatic pressure. Atmospheric pressure given in the question, 101 times 10 to the 3. And then the hydrostatic pressure is rho GH. We know that H is 20 and we know G is 9.81. And we know that in this instance, rho is 1.03 times 10 to the 3. So our total pressure is 3.03 times 10 to the 5 pascals. In our next question, we know that the mercury is going to exert a pressure of rho GH. Pop in all the values. You've got the density, 1.35 times 10 to the 4. We've got the height, 0.765. And we've got G to be 9.81. So it's 1.01 times 10 to the 5 pascals. And then finally again, pressure is rho GH, so it's 1.03 times 10 to the 3 times by 9.81 times by 610 is 6 times 10 to the 6 pascals. The next question says, calculate the pressure of the water on the bottom of the swimming pool if the depth of the water in the pool varies between 0.8 meters and 2.4 meters. If the atmospheric pressure is 1.01 times 10 to the 5 pascals, calculate the maximum total pressure at the bottom of the swimming pool. Then estimate the height of the atmosphere if the atmospheric density of the Earth's surface is 1.29 kilograms per meter cubed. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first question, what do we know? Well, we can work out the pressure at the depth of 0.8 meters by doing rho GH, popping all the values in, and we get 7.85 times 10 to the 3 pascals. We can therefore do the pressure at 2.4 meters, and we work it out to be 2.35 times 10 to the 4 pascals. So therefore the maximum total pressure is going to be the one at the bottom at 2.4 meters. We can add that to the pressure of the atmosphere because that's also pushing down on us. So we add the two together to be 1.25 times 10 to the 5 pascals. In the next question, we want to work out h because it asks for the height. So we can say P equals rho GH, so h equals P over rho G. Pop in all the values. We've got the pressure, we've got the density, we've got the strength of gravity. So we get 7,980 meters. But this value is actually a little bit too small because it assumes the density of air is constant when in fact the density of air will decrease with height. The next question says, a table tennis ball is held underwater and then it is released. Describe and explain the subsequent motion of the ball. Then the metal bar is suspended from a Newton meter. The reading is 1.54 newtons in the air, but only 1.34 newtons when the bar is fully submerged in the water. Firstly, calculate the upthrust on the bar, then secondly, the density of the bar. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, what do we know? Immediately after the ball is released, the ball will experience two forces as it's underwater, upthrust and weight. upthrust will be greater than the weight, so the ball will therefore accelerate upwards. As it travels vertically upwards, it'll also experience some drag due to moving upwards in the water. Now, as it pops out of the water, the only force remaining on it is weight, because upthrust will disappear as it's no longer in the water. So it'll decelerate due to the resultant force of weight and fall back to the surface of the water, and eventually remain still on the surface of the water, where the upthrust has now reappeared and it is now equal to weight. Now we can see our upthrust here is going to be the difference between the two values in this next question, because it's going to be that force acting upwards. So it's 1.54 minus 1.34, so it's 0.20 newtons. Now we can tell, because it's suspended and it's fully submerged in the water, that the upthrust must equal the weight of the water. So the mass of the water is going to be 0.20 divided by 9.81. So when we work that through, it's going to be 2.03 times 10 to the minus 2 kilograms, because we know weight equals upthrust, and then we for weight equals mass times gravity. Then we can say the volume of the water displaced is equal to the volume of the bar, because it's fully in the water, it's fully submerged in the liquid. So we can therefore say the volume is going to be 2.03 times 10 to the minus 2 over 1 times 10 to the 3. So it's 2.03 times 10 to the minus 5. Density is mass over volume, so you can work it all through, and you get 7.7 times 10 to the 3 kilograms per meter cubed. The next question says, Figure 5 shows an object held underwater. The density of the object is 400 kilograms per meter cubed and has a volume of 6 centimeters cubed. The density of the water is 1000 kilograms per meter cubed. Explain why the object experiences an upthrust, and then calculate the initial upwards acceleration of the object when it is released. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, the object will experience a greater pressure at the bottom surface compared with this upper surface, because it's further down in the actual liquid. So the difference in pressure produces that upwards force, which we call upthrust, and the upthrust must be equal to the weight of the water displaced due to Archimedes' principle. So with that idea, we can say that the weight of the object is equal to mg. So we know what our value of m is. It's going to be 400 times by 6 times 10 to the minus 6, because mass is density times volume. So therefore multiply by 9.81 to work out the weight. We know that the weight must equal the upthrust, so therefore we can tell that we can know that our upthrust is equal to 1000 times 6 times 10 to the minus 6 times by 9.81. So therefore our net upwards force is going to be 6 times 10 to the minus 6 times 9.81 times by 1000 minus 400 due to this change of this difference in density. So it's therefore 3.53 times 10 to the minus 2 newtons. Acceleration is force over mass. We've got our force, we've got our mass now, so we can say it's 14.7 meters per second squared. The next question says an ice cube is partially submerged in a glass of water. The bottom face of the ice cube is at a depth of 3 centimeters. The density of water is 1000 kilograms per meter cubed. Calculate the pressure acting on the bottom of the ice cube due to the water. Then a uniform cylinder is submerged in water. The radius of the cylinder is 5 centimeters. The top of the cylinder is at a depth of 65 centimeters, and the bottom of the cylinder is at a depth of 76 centimeters. The density of water is 1 gram per centimeter cubed. Calculate the upthrust on the cylinder. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, what do we know? We know that pressure is equal to rho GH. So it's going to be 1000 times by 9.81 times by our height, which is 0.03, 3 centimeters into meters. So it's 300 pascals. Now we know upthrust is going to be the difference in the heights times by rho GH times by area, because we know that pressure is rho GH, and we know that force is pressure times by area. Now we know area is pi r squared because it's a cylinder, so we therefore will change our 5 centimeters into meters and do pi r squared. Therefore we know the upthrust is the change in height in meters, so 0.760 minus 0.650 multiplied by the value of the pressure times by the gravity 9.81 multiplied by that area, and we get our upthrust out to be 8.48 newtons. Now the following question says, figure 7.8 shows the force extension graphs for 4 springs A, B, C and D. Which spring has the greatest value of spring constant? which spring is the least stiff, and which of the four springs does not obey Hooke's law. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can tell you that D has the greatest value of spring constant, because in the force extension graph, the gradient is the spring constant, so D has the steepest gradient, so must have the highest spring constant. Spring A is the least stiff because it has the most extension for each unit of force applied, stiffness being the force per unit, the amount of extension per force placed upon the object. Okay, and then which of the springs does not obey Hooke's law? Spring C doesn't obey Hooke's law because to follow Hooke's law, force and extension are directly proportional, so you need a straight line section for your graph. The following question states a force of 6 newtons is applied to a metal wire, which extends by 0.040 meters. Calculate the force constant of the wire, and then calculate the combined force constant for 3 springs, where there are 2 55 newton per meter springs in parallel below one 75 newton per meter spring. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, we know that the force constant, or the spring constant, is the force divided by the extension. So it's 6 newtons divided by 0.040, which is 150 newtons per meter. Now in this next question, you can work out the spring constant when you have springs in parallel by adding the two together. So the two 55 newton meter springs in parallel will give you a spring constant of 110 newtons per meter. Now then we can work out when they're in series by doing 1 over the total equals 1 over K1 plus 1 over K2. So it's 1 over 75 plus 1 over 110, so you work that through, and K is 45 newtons per meter. The next question says, a shelf of mass 14 kilograms is supported by 4 identical wires. The original length of each wire was 1.800 meters. When attached to the shelf, the length of each wire is 1.804 meters. Calculate the force constant of each wire. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, firstly, what's the force in this situation? Well, the force is going to be the weight divided by 4 because there are 4 identical wires. So, the force is 34.3 newtons. So each wire experiences 34.3 newtons. Remember, it's 14 kilograms times by the strength of gravity, 9.81. Our extension is the difference in length, so 0.004 meters, and therefore we know F equals Kx, so therefore the spring constant K is equal to F over X, or 34.3, divided by 0.004, so it's 9 times 10 to the 4 newtons per meter. The next question says, a force of 12 newtons extends the length of a rubber band by 18 centimeters. Estimate the energy stored in this rubber band, and why can this answer only be an estimate? And then a spring has a force constant of 4,800 newtons per meter. Calculate the elastic potential energy when it's compressed by 2 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one, what do we know for elastic potential energy? Well, we know E is equal to a half Fx, so it's a half times by 12 times by 0.818, where again, remember 18 centimeters turns into 0.18 meters, so we get 1.1 joules. Now, it's only an estimate because we can only use this equation if we consider the rubber band to obey Hooke's law. Now in this next question, we can use the equation elastic potential energy is equal to a half kx squared. So it's a half times by 4,800 times by 0.0020 or 2 millimeters into meters squared. So we get 9.6 times 10 to the minus 3 joules. The next questions say, a metal spring has a spring constant of 1,250 newtons per meter. When a force is applied, the spring extends proportionally by 1.60 centimeters. Calculate the force applied. Then a spring is compressed proportionally 0.80 millimeters by a force of 20 newtons. Calculate the spring constant of the spring in newtons per meter. then the original length of a metal wire is 20 centimeters. A force of 55.0 newtons is applied and the wire extends to a new length of 22.0 centimeters. Assume that the limit of proportionality has not been reached. Calculate the extension of the wire in meters, and then calculate the spring constant of the length of the wire. And then calculate the combined force constant for 4 springs where there's an 80 newton per meter and 60 newton per meter spring hung from one from the other, and this is in parallel with another 80 newton per meter and 60 newton per meter spring hung from one another. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that force equals force constant times by extension, so it's 1,250 times by 0.0160 meters, centimeters into meters, so we get 20 newtons per meter. In the next question, we know the force constant is force over extension, so it's 20 over 0.8 times 10 to the minus 3 millimeters into meters, so we know 2.5 times 10 to the 4 newtons per meter. In this next question, extension is the change in length, so it's 22 minus 20 centimeters, which equals 2 centimeters, which turns into meters as 0.020 meters. Our force or spring constant is force over extension, 55 over 0.020, so 2.75 times 10 to the 3 newtons per meter. When we have, in this last question, when we have springs in series, we would do 1 over total is 1 over K1 plus 1 over K2. So it's 1 over 80 plus 1 over 60, 1 over that value is 34.2 newtons per meter. And when they're in parallel, we can say that we can add them. So therefore, it's 34.2 plus 34.2, because they're two identical components. So we get 68 newtons per meter. The next question says, figure 7.17 shows force extension graphs for 2 materials. For each of the following questions, explain how to deduce the answers from your graph. Which polymer has the greater stiffness? Which polymer requires the greater force to break it? And finally, which polymer requires the greater amount of work to be done to break it? So pause the video now, then unpause the video and you want to go through your answer. Right, in the first one, A has the greatest stiffness because it has the steepest gradient in this force extension graph. We know the next one is that it's going to be A. It needs a greater force to break it because it has a higher value of force on the y-axis. And then finally, B requires a greater amount of work to be done because that's the area under the graph, which is greater for B. The next question says, rubber is an elastic material. Explain what this means. Then, explain why a rubber band does not have a spring constant. Compare and contrast the behaviour of a metal wire and a strip of polythene. And then the figure below shows the force extension graph for a length of bungee cord. Use the graph to estimate the thermal energy released when the cord is stretched by 0.40 meters and returns to its original length. So pause the video now, then unpause the video when you want to go through your answer. Right, so what does elastic mean? Elastic means it'll return to its original length, its shape and size, when the forces are removed. It doesn't have a spring constant because the force extension graph for rubber is not a straight line through the origin, so doesn't obey Hooke's law, so can't have a spring constant. Now the metal wire has an elastic behaviour up to its elastic limit, but the polythene wouldn't show any elastic behaviour. The polythene will show inelastic deformation, as does the wire when it's stretched above its elastic limit. And in the figure shown below, the thermal energy dissipated is the difference in the two loops, so it's the area in between the two lines. So that is therefore, when you count it through, 4 squares. And each square, you can see, is 0.1 times by 10, which is going to be 1. So therefore, it's 4 times by 1, which equals 4 joules. The next question says, a spring is used to fire a toy rocket vertically up in the air. The mass of the rocket is 200 grams and when placed on the spring it compresses by 15 millimeters. Assume that the spring obeys Hooke's law. Firstly, find the spring constant. Secondly, the spring is compressed by another 20 millimeters. How much energy is stored in the spring? And then assuming that this was all transferred to the rocket, what is the maximum height of the rocket's flight? So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, the spring constant is going to be linked to the equation that K is going to equal F over X. So we know that F is going to be the weight, so it's 0.2 grams into kilograms, 9.81. Then we divide it by 15 times 10 to the minus 3 millimeters into meters. So therefore it's 131 newtons per meter. The elastic potential energy is going to be a half kx squared. We just worked out K to be 131. So therefore we do half times by 131 times by 0.035 meters, because again it's another 20 millimeters, so therefore it's 35 millimeters, which is 3.5 times 10 to the minus 3 there, so it works it through. So 35 times 10 to the minus 3, so it's 8 times 10 to the minus 2 joules. Then finally we're assuming all of this energy turns into gravitational potential energy, so therefore it equals mgh. So h is equal to, it's going to be equal to this value divided by mg, which we know to be 0.2 times by 9.81, so it's 4.1 times 10 to the minus 2 meters. The next question says, a spring balance used to weigh hand luggage needs to weigh objects of mass between 0 and 10 kilograms. Firstly, suggest a suitable value for the spring constant. Then the balance is used to weigh a mass of 5 kilograms. What would the uncertainty of the measurement be? And then a student says that choosing a suitable spring for a balance is a compromise between the precision of the readings and the maximum mass that can be measured. Is she right? Explain. So pause the video now, unpause the video when you want to go through your answers. Right, so the maximum load is going to be 100 newtons, and the extension of 5 centimeters will be very manageable for you to observe as a human. So we can say K equals F over X, 100 over 0.05, which is centimeters into meters there, so it's 2000 newtons per meter. We know that an uncertainty of 200 grams is going to therefore be about 5 plus or minus 0.2 kilograms, because roughly when it's going to be, if it's got 5 kilograms, roughly out by about 200 grams, so that's 0.2 over 5 times by 100, which is a 4% uncertainty. Now, a high spring constant would mean that a large mass could be weighed without stretching the spring too far, but this stiff spring wouldn't be very sensitive, so you wouldn't get a great variation in your results, so therefore the student is correct. The next question says a chest expander is made from 5 identical springs in parallel. When a force of 100 newtons is applied to the handle, the spring extends by 1 centimeter. Find the spring constant and energy stored in the springs when extended. Then secondly, Chris wants to increase the work he does in stretching the springs of the chest expander, so he dismantles it and connects the spring in series instead. He secures one end to the wall and pulls the other end with the same force as before, 100 newtons. Will this increase the work done? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question we know that because the springs are in parallel, that the force is shared between the springs. So for each spring we're going to say K equals F over X, and therefore the 100 newtons is spread 5 ways, so it becomes 20 newtons. So it's 20 newtons over 0.01, that's centimeters into meters there, so it's 2000 newtons per meter. We then know E equals a half Fx, so therefore it's a half times by 20 times by 0.01. So therefore for each of the springs it's 0.1 joules, so it's 0.5 joules altogether. Now in the second question, the force of 100 newtons is now applied to all the springs, so each is now a spring constant of 2000 newtons per meter, because it's the same spring and it's a constant. So we know X is F over X, so it's 100 over 2000, so therefore it's 0.05 meters. We then know the elastic potential energy is a half Fx, so it's a half times by 100 times by 0.05, which is 2.5 joules, so this means it's 12.5 joules altogether being used as your work, so more work is being done. The next question says a rubber band is extended by 20 centimeters by a force of 18 newtons. Estimate the energy stored in the rubber band. The energy stored in a stretched cable is 1.5 joules when it's extended by 2 millimeters. Calculate the spring constant of the wire. Below is a force extension graph for a spring. Calculate the work done on the spring when the extension changes from 5 centimeters to 15 centimeters. And then a spring of mass 8 grams has a spring constant of 120 newtons per meter. It's placed upright on a horizontal table and compressed by 4 centimeters. It is then released and jumps vertically above the table. Calculate the maximum height gained by the spring above the table and state any assumptions made. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first question, we know E equals Fx. So E equals a half times by 18 times by 0.20 centimeters into meters. So it's 1.8 joules. Our next question, we now have we can now work it through by doing E equals a half kx squared, so therefore k equals 2e over x squared. So it's 1.5 times by 2 over 2 times 10 to the minus 3 millimeters into meters, or the squared there, so it's 7.5 times 10 to the 5 newtons per meter. We can see that in our force extension graph, the work done is the area under the graph. So you can see from 5 centimeters to 15 centimeters, it's a half times by 0.10 times by 15 minus 5, which is 10. So it gets to be 1 joule. The next question, we can say that the elastic potential energy is a half kx squared, so it's a half times by 120 times by 0.04 centimeters into meters, so it's 9.6 times 10 to the minus 2 joules. We assume all the elastic potential energy will go into gravitational potential energy, so it equals mgh. H will equal this value divided by mg. We've got our mass to be 8 grams, so it's 0.08, which is grams into kilograms, times by 9.81, work it through, we get 1.2 meters. The next question says, list all the metals in the table from stiffest to least stiff, and then which of the non-metals is the stiffest. So, pause the video now, then unpause the video when you want to go through your answer. Right, you've got to be aware that the Young modulus tells you the stiffness of the material. So the most stiff is steel with the highest Young modulus, whilst the least stiff is lead with the lowest Young modulus. And it's the same idea for the non-metals. The highest Young modulus is the stiffest material, which in this case is glass. The next question says, figure 7.12 shows the stress-strain graph for two materials, A and B. Use the graph to determine the Young modulus of each material. Then a piece of steel wire 200.0 centimeters long and having a cross-sectional area of 0.50 millimeters squared is stretched by a force of 50 newtons. Its new length is found to be 200.1 centimeters. Calculate the stress and strain and the Young modulus of the steel, and then calculate the extension of the copper wire of length 1.00 meters and diameter 1.00 millimeters when a tensile force of 10 newtons is applied to the end of the wire. So pause the video now, then unpause the video when you want to go through your answer. Right, to be aware, you can work out the Young modulus for a stress-strain graph from the straight line section is gradient in that line. So for material A, it's going to be stress over strain for the straight line section, 15 times 10 to the 6 over 0.01, so we get 1.5 gigapascals. And then for B, again, it's the gradient of the straight line section, 12 times 10 to the 6 over 0.024, so it's 5 gigapascals. In this next one, we know stress is force over cross-sectional area, so it's 50 over 0.5 times 10 to the minus 6, remember millimeters squared into meters squared, so therefore it's 1.0 times 10 to the 8 pascals. And then the strain is the extension over the original length, 0.1 over 200. We can keep the same units because it's a ratio, so it's 5 times 10 to the minus 4, or 0.05%. So the Young modulus is stress over strain, so we work it through, it's 2 times 10 to the 11 pascals. In this next one, we know Young modulus stress over strain. So strain is stress over Young modulus, which is going to equal F over A times by the Young modulus. We can work out area because it's going to be pi times by diameter squared over 4. That's just a mathematical equation. Pop in all the values, work it through, and we get 9.8 times 10 to the minus 5 meters. The next question says, a sample of fishing line is 1.0 meters long and is a cross-sectional area of radius 0.25 millimeters and is circular. When a weight is hung on the line, the extension is 50 millimeters and the stress is 2 times 10 to the 8 pascals. Calculate the cross-sectional area of the line, the weight added, the strain in the line, and then the Young modulus. So pause the video now, then unpause the video when you want to go through your answer. Right, the cross-sectional area is pi r squared, so when you do that you will get your radius of 0.25 millimeters, so 0.25 times 10 to the minus 3 millimeters into meters squared times by pi is 2 times 10 to the minus 7 meters squared. The weight is going to be equal to stress times by area, because you know stress is force over area and weight is just force. So you can work it all through and you get 39 newtons. Strain is extension over length, keeping in the same units. It's going to be 0.050 millimeters into meters, divided by 1, it's 0.050, and the Young modulus is stress over strain, so that at that point you can do your stress, 2 times 10 to the 8 pascals, over the strain 0.050, it's 4 times 10 to the 9 pascals. The next question says, explain what is meant by the ultimate tensile stress of a material, describe the properties of cast iron from the graph below. Then a metal has a diameter of 0.20 millimeters, a force of 6.3 newtons changes its length from 1.035 meters to 1.048 meters. Calculate the Young modulus of the metal. Then the ultimate tensile strength of a metal is 220 megapascals. Calculate the maximum force that can be applied on a wire of diameter 1.2 millimeters from this metal. So pause the video now, then unpause the video when you want to go through your answer. Right, so the ultimate tensile strength of a material is the maximum stress that can be applied to a material before it breaks. From the graph below you can see that cast iron is a brittle material because you can't observe any inelastic deformation because the line does not curve. In the next question, we know stress is force over area. Remember, a wire we're going to assume has a circular cross-sectional area, so therefore it's going to be pi r squared. So we're going to take our diameter, half it, convert the millimeters into meters, work it all through, and we get our stress to be 2 times 10 to the 8 pascals. Strain is extension over length, so you work out your change in length for your extension, divided by the length, then you get 0.0125, and then the Young modulus is stress over strain, so it's 2 times 10 to the 8 over 0.0125, so it's 1.6 times 10 to the 10 pascals. We know that the ultimate tensile strength is going to work through to be a pressure, so it's going to be force over area. So therefore force is the ultimate tensile strength times by the area. So it's 220 times 10 to the 6 megapascals just into pascals, times by pi r squared. So again with half the diameter to get the radius, we've then converted the millimeters into meters, and then we work it all through and we get 250 newtons. The next question says, for each of the materials whose stress strain graphs are shown, deduce the values of the Young modulus and the breaking stress. So pause the video now, then unpause the video when you want to go through your answer. Right, so for material A, the Young modulus is the gradient of the straight line section, so you can work that through and it comes out to be 50 gigapascals, and the breaking stress is the highest possible value of the stress, which is 150 megapascals. For material B, again the Young modulus can only be found for the straight line portion of the stress strain graph. So therefore you've got to do the stress of the straight line section, which goes up to 100 megapascals, so that's 10 to the 6, divided by the strain there to get 100 gigapascals, and again the breaking stress is the highest value it goes to, which you can see to be about 130 megapascals. Then again for material C, it's the stress over strain, so the gradient of the straight line section, so it's 25 gigapascals, and the breaking stress is the highest value, 100 megapascals. The next question says, a steel girder is tested to find the tensile strain of the girder when a load is added. The original length of the girder is 5.00 meters. During the test, the length of the girder is remeasured. The new length of the girder is 5.04 meters. Calculate the tensile strain of the girder. Explain why tensile strain has no unit. And engineers need to inspect the metal girders of motorway bridges for signs of metal fatigue. One of the causes of metal fatigue is the large number of heavy lorries that drive over the bridge each day. Describe how heavy lorries can cause metal fatigue when driving over the metal girders. And the metal girders are made of steel. Steel is a malleable material. Explain the meaning of malleable in terms of atomic structure. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, strain is extension over length. So the extension is 0.04 meters. The overall length is 5 meters, so it's 0.008. It has no unit because the two distance units will cancel through because it's a ratio. Now, heavy lorries can cause metal fatigue because they'll deform and bend the girders each time they cross the bridge. The heavier the weight, the greater the pressure of the lorry, causing a greater amount of strain. So the total effect of deformation will increase over time until you get failure. Now, what happens in terms of malleable? That means that the atoms are in a lattice, so they're in layers, so therefore the layers of atoms can slide over each other when a force is applied to allow it to extend easily. The next question says, Figure 7.18 shows the force extension graph for a metal wire of length 2.0 meters and cross-sectional area 1.5 times 10 to the minus 7 meters squared. Calculate the Young modulus, determine the energy stored in the wire when the extension is 0.8 millimeters, and calculate the work done in stretching the wire between 0.4 millimeters and 0.8 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first one, we know that stress is force over area, so therefore it's going to be 10 over 1.5 times 10 to the minus 7. We've got the area given in the question, so it's 6.67 times 10 to the minus 7 pascals. The strain is the extension over the original length. Again, from the top of the line, we can read our extension. So you can work it through to be 0.4 times 10 to the minus 3. The Young modulus is stress over strain, so it's 1.7 times 10 to the 11 pascals. The energy stored is a half times by force times by extension. So we've got the force to be 10. We've got the maximum extension to be 0.8 millimeters. So it's 0.8 times 10 to the minus 3. So it's 4 times 10 to the minus 3 joules. And then the work done in stretching between 0.4 millimeters and 0.8 millimeters. Again, the work done is going to be the force times by the extension. So if you look on your graph, you can see the average force between 0.4 and 0.8 is going to be 7.5 newtons, multiplied by the extension, which is 0.4 millimeters, or 0.4 times 10 to the minus 3 millimeters into meters. So it's 3 times 10 to the minus 3 joules. The next question says, figure 7.1 shows the stress strain curves for the three materials P, Q and R. State and explain which material has the greatest Young modulus. Then describe an experiment to determine the Young modulus for a material in the form of a wire. Show how you would use your measurements to calculate the Young modulus. So pause the video now, then unpause the video when you want to go through your answer. Right, from the graph, P has the largest Young modulus as it has the steepest gradient. Now in this next one, you would have a label diagram showing a wire being stretched by weights. You would then think of a method to view extension, for example use a marker in a travelling microscope. You would then use a series of weights to cause this extension and note the extension and the weight placed upon the wire. You would then measure the diameter of the wire with a screw gauge micrometer, measure the initial length of the wire, and then graph force against extension, and then the Young modulus is going to be equal to the gradient of the force extension graph multiplied by the length divided by the area. The next question says, show that the Young modulus of a material can be calculated with the equation E equals FL over AX. Then use the equation to determine the Young modulus given that the diameter of the wire is 0.84 millimeters, the original length of the wire is 2.500 meters, the force applied is 300 newtons, and the extension is 1.4 centimeters, and then state one significant assumption made in the previous calculation. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know that the Young modulus is stress over strain, stress is force over area, strain is extension over length, so when you work it through, it's F over A times by L over X, so therefore it's FL over AX. We can then pop the values into the equation, so it's 300 times by 2.500 over pi r squared. So we take our diameter, we half it, we then turn millimeters into meters to work out our area. We then multiply by our extension, again centimeters into meters, so 1.4 times 10 to the minus 2. So we get 9.7 times 10 to the 10 pascals. And our assumption is it's a straight line in our stress strain graph, so therefore the elastic limit of the material has not been exceeded. So stress and strain are directly proportional. The next question says, an object of weight 790 newtons is suspended vertically from a crane on a steel cable 4 meters long and 6 millimeters in diameter. The Young modulus of the material of the cable is 2.0 times 10 to the 11 pascals. Calculate the extension of the cable. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this question? Well, we know firstly stress is force over area, so it's 790 over the area, so it's pi r squared. So we take our diameter, we half it, we turn millimeters into meters, and we work out our area. So our stress is 2.8 times 10 to the 7 pascals. The Young modulus is stress over strain, so therefore strain is stress over extension. So we work out our strain, because we've got the Young modulus and we've got the stress now, to be 1.4 times 10 to the minus 4. Therefore, extension is going to be strain times by length. So it's 1.4 times 10 to the minus 4 times by 5, which is 7.0 times 10 to the minus 4 meters. So the following question says, a crane raises loads from the ground using a cable as a diameter of 0.024 meters and a length of 25 meters. The Young modulus of the cable is 70 times 10 to the 9 pascals. Calculate the amount the cable extends when raising a load of 3,600 newtons, ignoring the weight of the cable. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, the first thing is we want to work out the area. So the area is pi r squared, so you turn your diameter into a radius by halving it. You then say pi r squared, so you get your area out. You then say stress is force over area. So it's 3,600 over 0.0045, which is 8 million. We then say Young's modulus is stress over strain. So we can therefore say that strain is going to be stress over the Young modulus. We've got already our value for Young modulus in the question, so we can work through to be 1.143 times 10 to the minus 4. We therefore know strain is extension over length, so therefore extension is strain times length, so it's 1.143 times 10 to the minus 4 times by the length that started with, 25 meters, so our overall extension is 2.86 times 10 to the minus 3 meters. So that brings an end to our revision session today. If we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our own understanding on A-level physics, understand what topics we need to improve upon for A-level physics. So thank you so much for watching this revision session for OCR A-Level Physics on the subtopic of materials, which is part of the module forces. So thank you so much for watching, and I hope you have a lovely day.